So hello everyone, I'm Kevin. I work at the Army Research Lab, and today I'll be kind of telling you a little bit about the kind of approach that we've taken to using Influx, our products, to give you some context for what we're doing. Then I'll be talking to you about how exactly the technical details of what we're doing, and then I'll step back a bit and show you some cool applications that we've used it for. So this is a picture of the outside of our building. Our mission statement you can read here, but basically it's to discover, innovate, and transition science and technology to make sure that the Army is the best there is out there. In particular, we really focus on early concept ideas to prototypes and taking fundamental new science and new technology, transitioning that through demonstrations to partners who will then take that and make it applicable to the warfighter. But underneath everything that we do is this idea of a transition to the warfighter and to keep them in the front of our mind. So a little bit about me. I have a physics background, so if you see any weird computer science things up there and you're like, why did he do it that way? That's stupid. Please tell me, because I would like to know a better way of doing that. But I've done everything from geophysics to optics, NMR, and now we're doing electric and magnetic field sensing. In particular, I'm here because I started with Influx about a year and a half ago, and I really found that it enables this kind of rapid prototyping that we really like, and also it makes for great demos that you can really show and people can understand what you're doing. And it also enables collaboration between different people and different groups spaced out. So this is kind of the Army problem that we have. We have not only an IoT environment, but an Internet of Battlefield Things, or IOBT environment, where the network is contested, it's congested, and it's very dynamic. You have things dropping in and out. You don't necessarily know even if your nodes are your nodes or opponent's nodes. If this actually was really interesting to you, we have a whole program in it, and I can hook it with people who really do this. But one of the main things that you want out of this is you want actionable data. And in our team in particular, we do this low-frequency electric and magnetic field sensing. What that kind of, our current application area is non-contact power metering. So as opposed to traditional power metering, this has significant advantages such as safety and cost, and it really drives efficiency and resiliency. So conserving fuel and being able to do more with the fuel you have. We also have other application areas such as using environmental data as well. We're building a really interesting sensor array, and we've done some wide area field surveys using kind of our Influx stack. In particular, what it looks like is we're running it both on the edge and the cloud. This is one of our edge clients here. And then we replicate the data, always being sure to replicate the most recent data so that, again, that data that leads to the action is replicated first. These are kind of our range of sensors. So we have what we call the mobile unattended ground sensor here, which is a little ruggedized and also accepts traditional sensor inputs. Then we have our mobile power meter, which has the non-contact field sensors in there. And then we also have a rack mount unit where you can add additional processing modules and really go up to hundreds of inputs. But there's some common features between all of them. An 8 to 16 kilosample data rate. They all are running an FPGA next to Linux, so we do a lot of the raw data processing on the FPGA. Our common software runs across all of them, and they also have additional sensors, such as the IMU and GPS data. So not only do we use those, but we also interface with some legacy equipment, and the data processing that we can do can be either attached here or on a nearby PC or even in the cloud. Same with storage, and then the network. We like Wi-Fi for prototyping things, but a lot of our customers don't like Wi-Fi. They want either Ethernet or they say, you know, don't hook up to my network at all. Just put it there, measure the data, and then give me the results back. And then, of course, also cellular and 3G, 4G is another good communications options. And then analysis is, again, from the edge up to the cloud. A lot of customers are also like, just give me the CSV file out. I'll do my own analysis. So when we look at kind of the application space that we have to support thousands of combinations of this. And one of the ways that we do this is we run a lot of our software on the edge device itself. So this is the form factor. This is what the board actually looks like. It's a snickerdoodle board produced by Critical. It's got an ARM processor in the FPGA there. So compute-wise, a Raspberry Pi is like 4 cores running at 800 megahertz. This is 2 cores running at like 600 to 800 megahertz. So we're talking about half of a Raspberry Pi. But on this, we run a web server so that the customer can bring their own device and interface with it and configure it and actually start viewing their data. We also run a net manager so that they can configure it to whatever networking configuration they want, and then a process manager, which runs a plot server. And so our software sits underneath that, and it takes data from the sensor, runs it through processing module, and then a real-time visualization that they can see. Now, where Influx comes in is we run that separately, and we have other processing modules that take the data and show our data in Influx, but then that also supports some of the visualizations. Okay, so this is what our data looks like. This is the raw data coming into the sensor. It's sampled again at 8,000 to 16,000 samples per second. We're talking 8 to 16 channels, which full data rate is 64,000 to 250,000 samples per second. That's a lot. Thankfully, we don't actually have to store all of that data. We can use what's called the synchrophasor standard to take this AC 60 hertz waveform and sample that to something called a phasor. What that is you look at the RMS magnitude, and you look at the phase offset between that peak and some timestamp, which in our case is GPS time. And so those two measurements then map to this phasor where you have an amplitude, and then it's offset from the x-axis is the phase. So now we've dropped that to something that's more like 10 to 60 hertz of 8 to 16 channels per data. However, we monitor not just the fundamental 60 hertz data, but also a couple of harmonics, the frequency deviation from 60 hertz, and the total harmonic distortion as well. And then these values are now complex, so you have to store twice as much. So you end up putting about 1,000 to 10,000 samples per second into the database, and we want to store all of that at the edge. So this is what our data looks like once we actually put it into a power system. You now have typically three-phase power, which means that you have voltages that are offset by about 120 degrees. And then, of course, this is just the voltages. You can imagine that for the currents as well. Okay. So this is what our processing stack looks like. We take real data or simulated data, throw that into something that standardizes it into what we call DLAMP packets, and that makes it available to kind of our historical architecture and processing system. Then after a little bit more processing, we use a Python module to shove that via the HTTP API into Influx. Then we run additional processes, such as for the IMU, the GPS, the battery, that shove more data into Influx. And then when there's a network available, we can replicate that data to the cloud. So one of the things that we like about the schema is it's a NoSQL storage, so it's really easy to get going. And it's easy to just throw in a new measurement and start taking new data. And you can also experiment with your schemas. So I went through about 5 different schema configurations before I found something that seemed actually very intuitive for power data. Of course, then if you have some software that's expecting a particular schema and it doesn't get it, things fail. So you have to compromise and find that in the docs. Some other things that we've noticed are that it does enforce type consistency. So if your client accidentally sends a float that looks like an int, that point gets dropped. So we have to explicitly cast everything to floats, and then I don't have to worry about it anymore. Our replication schema is also kind of interesting because we want to duplicate it identically on both the edge device and the cloud so that we can develop for either of them and then port the processing software to the other location. And then, of course, you guys know all about downsampling and backups and restore. So this is what kind of our replication schema looks like. So what it does is it's a separate module that queries a database for particular measurements. And so it captures the latest endpoints, and then it marks that region in a new measurement as, hey, I've replicated this measurement over this time period. So that's good. And then when it does its next pass, it doesn't want to have to redo that. So it grabs the latest data again and then goes further back in time. And then it marks this new region as replicated. So that's great, but now we've got 2 regions that are marked as replicated. So what do we do there? Well, when we first query these replicated regions, we then modify one of their tags to depreciate one of them as say, this one's overlapped. And then we capture, again, the latest endpoints with, if n continues to overflow back in time. And this way, we can rapidly go through and claw back all the historical data while maintaining the fact that our most recent data is always being pushed. One of the interesting use cases for telegraphs I found was, since our system's so small and every CPU cycle is valuable, we actually use telegraph as kind of a performance tester. So this is different components of our processing stack booting up. And this is that influx inserter running at a couple of different settings. So this is it running at the full, actually this is about 16 hertz insertion rate, and this is turning it down to 1 hertz insertion rate, right? So this is using way too much CPU for me. So I'm like, okay, well, this is clearly the part that we need to optimize because I want that full phasor rate data. So looking at that, this is now, this graph shows the CPU consumption for 2 different ways. The red is the initial way I was doing it, where I was just basically collecting data for all the different series and then sending that to Influx all at once and be like, okay, here, parse this and put it into the individual series yourself. And the green is now where I'm actually tracking the series individually, and then I do bulk writes by series into the database. And as you can see, that really dramatically improves the performance there in the CPU. And that might be partially the Python client thing. Doing the bulk writes in series might alleviate some of the escaping that needed to do there. So now that we kind of know what the bulk CPU usage looks like, let's kind of break that down and decide, well, is that our processes or is that Influx that's using all its CPU? So that's shown over here in this graph. So now this is the processes, Influx is here. This is the one that does the insertions. So red was the old schema way of doing things. Blue is the new schema way, so you can see that we've actually saved quite a bit there. And then additionally with some of the other modules. Now you can see that actually the replication, red was the old way, which is a completely different algorithm that I didn't describe to you because it was pretty opaque and pretty difficult to maintain. The new algorithm uses more CPU, but it claws back the data faster and does so more effectively. So even though it's using more CPU, I'm actually happier with it. And you can see the total CPU usage is still about a wash. Now the difference between the blue and the green bars is that in this case, I've now enabled compression. So we're at the edge and we don't want to necessarily send up a ton of data, so we want to compress the data. For me, this was actually really fun because this was my first open source contribution to the Python InfluxDB library. So it was about 6 lines of code here. The tricky part was making it Python 2.7 compatible. But once it's working, it's actually working pretty decently. These are some different measurements going from CPU, disk, memory, system, battery. And then these are our PHASOR measurements here. So you can see some of them compress really well, like disk, and that kind of makes sense because you've got the slow uptick in data. Also, line compressions, or line protocol lends itself to compression very well because you've got a bunch of repeated tag and field measurements. And then these values here are about a factor of 7 compression. But for us, it's great, especially when you're dealing with a 4G network and you're talking about whether you're going to go over your data plan or you're not going to go over your data plan. Cool. So now that I've drilled in those technical details, let me take a step back and talk to you about some of our application areas. So I already touched on this. This is the mobile power meter. The idea is to replace something that looks like this, which is a power box. And here, what you need is you need an electrician to go in with a measurement device, which are fairly cheap, but the electrician costs a little bit per hour. But the main cost driver here is the fact that if the electrician is going to do this safely, they have to do a power interruption. And depending on what's on the other end of that power box, that interruption can be very costly. If it's a command control or a hospital, you don't really want to necessarily shut down power even, in which case your electrician now might be operating on a live system, and now he's put his health and safety at risk for doing that. So our solution is to monitor the fields that are put off. So when you have a voltage, you get an electrical field. And when you have a current run, you get a magnetic field. So you can measure both of those, and then you can do a calibration back to the voltages and currents. And that's what we do. So now you don't need that power interruption, and you've driven the main cost driver down to 0. And so the impact is that now this resource that you're having, you're now monitoring it. And now, of course, everybody knows once you're monitoring something, you can start to optimize it and really save energy, save fuel, and save lives because fuel, trucking that to the 4 operating bases is a dangerous proposition. Okay. So this is kind of what that looks like. Now, this is a 3D computer simulation of a microgrid cable that this sits on top of. And you can see the electric field around one of those conductors. So the thing to note here is that as you go around that conductor, that electric field changes, which means that your calibration now needs to be recalibrated. So in this case, we're starting to insert IMU data so that if it gets kicked or moved or a truck rolls over it, it can now alert us that it needs to be recalibrated, or ideally alert an automated system that would need to be recalibrated. Also, as a researcher, throwing the IMU data into it was advantageous. Previously, in order to kind of, this is taking the sensor and moving it all the way around the cable. And so to do that previously, I would move it around and then some, and I'd say, okay, well, it overlaps here, and I must have been going at a constant rate, which I really wasn't. But if we assume a constant rate, then we can say that's what it looks like over 360 degrees. As a result, you get these really jagged lines that don't really line up on each other. But once we throw the IMU data in there, then we know exactly what the orientation of the device is, and you can get much more reproducible measurements except when you drop it off the cable. So that's really facilitating new science for me. One of the other cool things is this is a project that a summer student did. This was basically, the idea is to monitor power into a building and use that to promote efficiency. So can we determine, for example, when the building has a door left open and then alert someone to say, hey, go close your building, you're losing AC power? Or can we look at a bunch of like barracks, for instance, and say, you know, this one's the least efficient barracks, let's go ahead and renovate that one so we have the highest ROI. So what the student did was they set up a light on a box here with a heater inside of it, and then ran a few different test conditions. And so this is looking at external temperature versus the duty cycle of the heater. And then they used a machine learning classifier to classify it as either was it lid open, baseline condition, or lamp on condition. So this was pretty successful, and we wanted to continue this project. The next instance was we took our sensor unit here, which is monitoring power, and then they got a Raspberry Pi and they hooked it up to an AC control. So now they have full control over the AC unit, and they can basically run it at whatever duty cycles or intervals they want. And they also log temperature, humidity, light. And so this is all on the same wireless network. So they shove data actually into our instance of InfluxDB. And then from our UI, they just go down here and check, hey, replicate this new measurement, go, and the replication script immediately starts replicating that measurement to the cloud. So this is what version 2 of that experiment looks like. It's shed out in Arizona. So as you can imagine, that AC unit's going to be working pretty hard. There's the AC unit. There's our unit and the Raspberry Pi. And then it sends data via Jetpack up to the cloud. And this is the chronograph instance where we can see the data. And actually, this is really neat for me because now that the student's back at ASU, we have weekly telecons, and he can call me up and be like, hey, Kevin, can you take a look at this data? And I'll be like, yeah, sure. And pull up exactly the same data, and we're both looking at the same events going on there. So that's been really nice for collaborating. This is another really exciting project we have. This is an imaging array. So here we have what we call a magnetic field cage. What this does is it creates a very uniform region of magnetic field. And it's a large region so that we can put entire sensors or entire platforms like quadcopters in there. But then what we want to do is we want to say, can we image with these magnetic or electric fields? And so that's what this array is. This is, in this case, a 4x4 array, but as you can see, we're expanding it. And it's made up of these 4D sensor pixels. Each pixel has a 3-axis magnetic field sensor in it. So it's measuring X, Y, and Z in the magnetic field, and it has a single-axis electric field sensor on it. We also have, oops, that's not a button. We also have an analog for the electric field. So this is the electric field sensor array sitting in our electric field cage. Again, the cage is designed to have a large uniform volume of electric field. And the sensor modules sit behind there, and this is a 6x8 array. And we have kind of an edge array of pixels to absorb the fluxes, the electric flux as it goes around the array. This is how the processing looks. We take the data from those pixels, it goes through a conditioning board. We do our standard phasor processing, and then we shove this is on the rack, so it shoves into a Intel i7 here, into the database there, and then we can query that database for visualizations. This is what our visualizer looks like right now. This was running that 4x4 array. It's pretty neat. We designed it to have N by M arbitrary arrays, and they can be sparse because we're thinking about taking the arrays out of the lab and testing them in the field. It does live visualizations of all of the parameters that we're looking at, including both magnitude and phase. And in fact, it can actually be run on the edge devices themselves. The dirty secret here is I'm not really a SQL guy, so it was actually really hard for me to start making the queries to pull data for this from Influx. So while we're shoving all of the data to Influx, it was easier to just take our packets and for me to reshape a matrix into a matrix. But I think actually for version 2, because this is operating at fairly low frequencies, at 60 hertz, a couple of degrees of phase error is a few hundred microseconds. But as we push our frequency up and we start looking at 300 hertz or 3 kilohertz or 30 kilohertz, now phase errors are going to be more important. So we need to have our data timestamped in the database accurately so that we can interpolate between times so that all of the phases actually line up. This is also a really fun experiment. We took one of those 3-axis magnetic field sensors. We added a 3-axis electric field sensor, and then we strapped it to the top of a car with our sensor processing unit here. And then we drove it around. This allowed us to measure basically power signals as we were going around. By having the IMU, though, we were able to orient those power signals to world coordinates. So while the car might have been moving left and right, up and down. We can transform those coordinates so that they're all the same coordinates, and then we can geo-register those so that as we drove around the installation, you can now see our vector fields as we're driving aligned with the world coordinates. And we think this is really neat. We're planning on proposing it for something like disaster recovery in Puerto Rico or the Bahamas, where you could then mount this on like a UAS, like a quadcopter, fly it over an area and get an idea for what the power infrastructure is, where it's been damaged, where you need to concentrate your relief efforts. And also, we're using it for background measurements. So I actually have recently, last week, took a survey of a field site, and we're geo-registering those coordinates so we can find the area with the lowest, basically, interference noise and then set up our experiments there. Cool. Now they actually asked me, hey, don't make it all, roses. What's some of the problems that you've had? And I guess I've got a couple of problems, one of which is, how do I find a good configuration? A lot of the Influx installs are great out of the box, especially if you're running on a server environment, but as you start pushing that down to these resource-constrained environments like a Raspberry Pi or a Snickerdoodle, you start having some issues with that. So there's definitely some good community there. I found this whole disable the internal logging, that actually got the database running, and the TSI1 index is really good, especially if you don't have a lot of memory to read through all of your shards. We've had this issue with a hard power cycle where, because our devices are edge devices, somebody pulls the plug and it shuts off. You don't get that SIGINT. You don't have an opportunity to finish flushing your data. And so that ends up corrupting a lot of these files. And Influx will try to recover a few of them, but then fail. And actually, I was just talking to Jacob earlier today, and that might be fixed already. So perhaps this isn't an issue. Some of the other things I've noticed is that if you're going to query into your database, again, on these constrained devices, you want to optimize those queries. It's best to fully specify that query. And then you can actually query quite deep in time and get a response fairly effectively versus trying to query across your series. Even a shallow slice of time can take a while. I don't know if anybody here is a Python and NumPy and Pandas fan. I am. I'm still not quite, don't have a good way of getting data into Pandas arrays. And then people have also talked here about how to map data into other data structures, like an image data or a Fourier transform, and look at Fourier transforms over time or images over time. This work is not done in a vacuum, of course. I'd like to point out this is our team. This is our team lead, David Hull. Brandon Parks did a lot of the data transmission protocols. Sean Heinzelman does sensors and a lot of the systems. This is Ross Edelman. He did the high-performance computer modeling. There I am. This is Alex George. He does the hardware design. He's a mechanical engineer. These are three of the students that we've had work on these projects. This is Zachary Drummond. He did the environmental sensing weather data project. Abby Snellman did a lot of the development of the embedded IoT system, which, by the way, we're open sourcing. And this is Kathleen Cohn, who did a lot of our unit tests to make sure that things don't fail out in the field. So anyway, I guess in conclusion, I actually really like Influx because it allows us to do a job more effectively, and it's this reducing time to awesome type thing, right? So we can basically come up with an idea, concept for an experiment, start shoving data into it, and then query that back out and do data processing fairly easy. The visualization also really helps for demos, and generally just helping to quantify things makes it so you can optimize them. The neat thing that I'm looking forward to is using some more of these capacitor alerts, especially for the transitions to the warfighter, right? The warfighter doesn't care about metrics, he cares about what should I do. And so the alerts are more of a, this is what you need to do. So we're looking forward to using more of those. There are, of course, some downsides. There's some hidden gotchas in the file corruption. So anyway, that's, if this is something that is interesting to you, please reach out and contact us. We're always looking for more people to join the team or to collaborate with. We've got multiple methods of collaboration. So if you have any questions, please, I'm here to answer them. Thanks. Microphone, I think.
Initially, I thought you said something about ingesting like points into the InfluxDB at around 1,000 to 10,000 hertz, but then later you said at 16 hertz. Is that the 16 hertz? Is that batch data of the 10,000 hertz, or was I misunderstanding something there?
So here, right? Yeah, so we're looking at 1,000, 10,000 hertz of raw data. So we timestamp it when it comes in, and then we batch that up and insert that about every second.
Oh, like 1 hertz you're batching it to?
Mm-hmm.
Okay.
Yeah, yeah. But once it's in the database, right, it corresponds to the actual 10,000 hertz, yeah. Great. Well, I guess if there are no other questions, we can invite our next speaker up. Thanks.